In the last section, we were looking at one-dimensional motion. It was either in the x direction or in the y direction. For this section, what we're going to do is we're going to focus mainly on objects that are launched at an angle or they're launched from some height and they follow a parabolic path. And think about this. I mean, you've all seen this before, the path of motion like this. Say you're on a ledge or you're somewhere above ground level and you kick something off. The motion it would take is it would fall off the ledge like this and it would start to curl toward the ground, like a parabola. Okay, you would fall toward the ground like that. Generally, we're talking about projectiles in this section, and we're going to be looking at objects that move to start either out or up. Either out or up. Sometimes you can talk about them being thrown down at an angle, and that works too, but that's not as common of an application of something. Why is it important to study stuff like this? I mean, think about any application of a projectile. Projectiles are everywhere. You cough, it's projectiles coming out of your mouth. Gross, yeah. You play sports, it's projectiles. You go for you go somewhere around the world on an airplane, it's projectile motion. All the laws you're learning here apply to things that you see all the time. Now, obviously, we're going to use what are called models and modeling with problems. So I'm going to say stuff like, an object is kicked off a ledge at a velocity. You need to think about what that means. What could that actually be? It's not necessarily just an object, but I'm not going to say like, some of these I'll say an airplane takes off at this speed, this angle, blah, blah, we'll figure out the values of the max height, the time of the flight, all that kind of stuff. But in these cases, we're going to look at problems that are really just models of the concepts that can be expanded upon in a larger scale. Again, physics, I keep talking about this. Physics is like the intro to getting into science and engineering and applying math. So if this interests you, projectile motion specifically, if you study something like engineering in college, you take an entire course on projectile motion. It's called dynamics, really. Okay? Objects in motion, objects moving free through space or on the ground level. But the idea here is that this is only a tidbit of what you guys could expect to see if you want to study this a little bit deeper. So we're going to talk about components again, and we talked about components in the last section, which makes this a little bit easier to look at. We're going to talk about the path of a projectile and then look at actual math involving projectiles. So some simple definitions. Okay, any object that can be modeled as a point in space, a point. So for example, a rocket takes off and you follow it through space. Well, a rocket has dimensions to it. You don't actually, if you're modeling it, just looking at projectiles, you don't actually care about the size of it. You care about what's called the center of mass. And you imagine that all the mass is concentrated at that location. So imagine if you had a truck, an 18-wheeler. A truck is huge, right? Well, where do you think the center of a mass of a truck would be? And this is an open-ended question. There could be several answers depending upon your interpretation. Where would the center of mass of an 18-wheeler be? Where would the center of mass? Like the center of mass of a human, you look at a human torso, you carry more weight in your legs or in your upper body? What do you think? Honestly, what do you think?
Legs.
Legs?
Upper body.
Upper body? Well, I would say it depends. Depends on the person. You've seen people with huge upper bodies and bodybuilders and then tiny legs. So theirs would be upper body. But then you see soccer players with enormous legs and not like huge upper body. So theirs would be low. So the center of mass is a function of the actual object. So think about like a truck. A truck itself, an 18-wheeler, if that truck is packed with Poland Spring water bottles filled, ruining the earth one day at a time, we'll see that the center of mass would be located toward the back of the truck. But if it's an empty 18-wheeler, the center of the mass is probably located closer to the front of the truck where all the actual mechanical components, the engine, are all located. So center of mass is a function of the actual object. We're going to model it as a point in space, okay, a single point in space. So this person that's running and then jumps from like a long jump is a great image from an old textbook. I know, it's like one of those 1980 things. She's running and stuff, and she runs for a long jump and jumps. Well, she's jumping up and she's jumping out. But we're not really modeling the entire body. We're modeling, for in this case, this is the origin right here. We're calling that the origin. That would be the center of mass. So the vector extends from the center of mass of a person or an object. So if you drew a box, and later on we're going to talk about free body diagrams, you would draw your vectors right from the center of the box, assuming that it's equally distributed weight. Okay, so imagine like a cardboard box that's empty. Where would the center of mass be? It would actually be right in the center, assuming that all the sides have the same amount of cardboard and tape and stuff.
When would it not be in the center?
Well, what I'm saying is that there's always a center of mass for all objects that exist. For any object, we prove mathematically, any object has a center of mass. It's where it's located depending upon the actual distribution of the object. For example,
So it's not always like in the middle.
correct. For this, it would be actually smack in the very center of this. Is there actually any material in the very center of this? No. So the center of mass, believe it or not, is a point in space in which it doesn't actually have to be on the object or part of it. It might be empty space. Now, for an example that wouldn't have a center of mass, that would be normal right here. I mean, this Purell is only filled up to like 3/4. So the center of mass, I'm going to tell you, is definitely below this line of Purell. It's not in the middle here. And this is only the middle of this container. Now, maybe because of this piece of plastic up here, the center of mass is close to the middle. But because of all this fluid, it's got to be a little bit lower. So the object has a center of mass that exists inside of it, whereas the other one was empty space. So for projectile motion, we're going to talk about a free fall with initial horizontal component or just two-dimensional. And what I mean by that for free fall with initial horizontal component, let's see if I have. So all it means, obviously, so for two-dimensional motion of an object that's not just launched straight up and down one-dimensionally or moving left to right, thrown at an angle, or launched at an angle. The second possibility is that it's technically free fall with horizontal velocity. Let me think about this for a second. If I roll this from left to right, does it have velocity in the x or in the y? Which one? X, right? Left to right. Up and down would be y. All right. So as I roll this, it's only in the x. So if I roll this right off the table, when it falls, it's pretty much the same thing in the y direction as just doing this and dropping it. Because think about it. Initially, as it's falling off the table, what did you just tell me? What kind of velocity did it have? It only had x, right? It didn't have y velocity at all. So the initial velocity in the vertical direction is technically 0. That's where that comes from. Free fall, that's what a free fall is, with an initial horizontal velocity component. So this, again, if you guys over there can see, obviously, it falls on a parabolic path. It's a projectile once it leaves the table. What causes projectile motion? What is it? Gravity. Without gravity, you wouldn't have projectile motion. You throw an object, what would happen? Obviously, you couldn't even throw it, but what would happen? Yeah, it would keep going forever, obviously, okay? If there was no gravitational pull from planets. So gravity is really the one thing that causes projectile motion. So what you can think about is this, and these concepts I'm talking about right now are really important to understand. We're going to apply them mathematically. The object itself is only undergoing a vertical force, not horizontal. Like I'm rolling this fine, back and forth, okay? Now, I let go of it and roll it off the table. Yeah, I gave it a force initially. But once I stopped, and once I let go of it, now it's moving on its own. Technically, there's no resistance. There's some friction on the table, obviously. But we could say that the velocity is pretty constant the whole time in the x direction. It doesn't look like it's changing very much. So the effect of gravity is on the vertical motion of the ball. The horizontal motion, whether I rolled it or threw it, would be the same. And that's kind of weird to think about. So let me explain here. Right here, I roll this like that versus tossing it like this. Horizontally, there was velocity this way the whole time. It didn't change. It's the exact same scenario. But vertically, think about it. What happened here? What kind of velocity on the way up would you say it has? What kind? Positive. And then what happens? Negative. And that's all in the y direction. In the y direction. But in the x direction, what's happening? The whole time it's moving like this. It's moving that way the whole time in the x. So the x velocity is always positive in this case. But the y velocity is positive, 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 slowing down, slowing down, slowing down, slowing down. 0 y velocity. It still has x velocity. And then negative y, more negative, more negative, more negative as it falls down. But at the top is when it pauses in the vertical direction only. So in these problems, since you guys have looked at formulas with x and formulas with y, we're going to break up our two components separately, completely. We're going to do them independently and then link them together in the end. So you have to think about what we've been talking about with components with vectors, because that's really what this is. So again, this person jumps at an angle. At an angle means partially in the y, partially in the x. That's what that's showing there in the diagram. Okay. We talked about this already. What is the difference in the two projectiles or the paths? What do you think one is accounting for that the other is not? What do you think one of these may be accounting for while the other is not? What's something we might say, we could kind of consider that negligible. It really doesn't affect the motion. But in reality, it does, and that's what this diagram is demonstrating.
Would it be like the angle of one tail or head?
That's a good idea. So one could be the angle. I could totally see that. One shoots at a higher angle, one at a lower angle. So the higher angle goes a little bit further. That's one possibility. There's several answers to this. So what I want to get your opinion.
Like wind?
Air resistance, wind, the blue path, assuming no air resistance, the black path, assuming that there is air resistance. Yeah, maybe the ball itself is different. They look different shades, so maybe the mass affects it. We're going to assume now, so this is why I wanted you guys to say all this stuff. Good. We're assuming the angle does affect it, so we'll talk about that. We're assuming the mass doesn't affect it, and we're assuming air resistance doesn't affect it. So we're not going to take into account air resistance, which you really should. That would affect your horizontal velocity. If I'm running, doesn't the wind push me back or doesn't air push me back? So technically, although I said in the x it's not changing, the velocity really is changing in real life. But unfortunately, until you get to like the end of pre-calc, the beginning of calculus, the math involved with drag force, believe it or not, is called what's a derivative. And it involves a little bit of calculus. It's not extremely hard, but for the sense of any high school physics course, you assume air resistance is negligible. Even AP physics you still do, which is kind of interesting to think about. First time we actually started including in engineering was when I was in like my sophomore year in fluid mechanics, because you study fluids and how they resisted motion. But it's really much more difficult, so we're going to assume for now that there's no air resistance. It makes the problems a little bit easier, more reasonable to handle. All right, so let's talk about this for a second. Actually, I want to wait on this, because I have an idea. I bought a cool new apparatus, and I want to show you guys something. But I haven't had a chance to set it up, so I'm going to come back to this in a little bit. Okay, I'm going to come back to this diagram in a moment. So let's look at this first example. A bridge is 300 meters above a river. So I use Tom Cruise a lot in these examples. I don't know why. This is like 3 years ago. I started making problems up, and I was watching, I think, what's the new movies he's in now? Reacher? Jack Reacher, yeah. Yeah. Oh, yeah. So I remember I saw when I was younger, it was Mission Impossible. Remember those? Yeah. Like 1, 2, and 3. So I always thought of him as like a nut. So I'm thinking about in this case. And then when he went on Oprah, and he went crazy. So this is just great. So Tom Cruise jumps off a bridge to avoid a sticky situation he's got himself into. He jumps off the bridge by running off the edge in the horizontal direction. In the horizontal, right? You got to know your words. Vocabulary is extremely important in this class. He's running horizontally. Now, if he hits the surface of the water after a horizontal, keyword, horizontal displacement, another keyword, of 50 meters, what is the velocity with which he jumped? What was the velocity with which he propelled himself off that ledge? So the best thing to do in these problems is to start with a diagram. It really will help you. Visualize what's going on. So here we go. We've got the bridge up here. We've got the body of water down here. And we've got Tom Cruise up here. Okay? He runs, and it says clearly, we have to look at our words here. It clearly says that he runs with a, where is it? Horizontal, in the horizontal direction, after a horizontal displacement. And the bridge itself is 300 meters above the river. Those are the key words that we have to include in our diagram somehow. So let's label our diagram. So where would 300 go? Where would I draw 300?
Right behind the bridge.
Yeah, between the bridge and the water. Agreed. What else can I label? What else? George?
Like he's 50 meters, I guess, like out into the water.
Very good, George. 50 meters out is where he lands, so we can draw the path already. So this is pretty much our situation right here. Now, there's one last piece, is that he's running in the horizontal direction. So remember I rolled the softball off the table a moment ago? When I rolled the softball off the table, you guys all agreed that the velocity of the ball was only in the horizontal direction. It was only in the x, and I agree also. Again, roll it back and forth. This is only in the x direction. As soon as it leaves the table, it starts to pick up velocity in the y. But initially, what's the velocity in the y then? If it starts, 0. It starts to pick it up. Again, right now, x direction only. So the instant, remember I talked about this like with impact velocity? It's the instant before it hits the ground, it's the velocity. So you're measuring, VF right there. Then it hits the ground. It's the instant before. Well, it's the same thing here. So Vx, the horizontal velocity, is the velocity the instant before it leaves the table. Then once it leaves the table, it starts to pick up vertical velocity, and it has a velocity at an angle now, right? Okay, so again, it's only in the x for a while, and then both in the x and y after it falls. So what that allows us to do is this. It allows us to say the following. We can assume in the y direction vi is 0. So let's draw two directions. Let's make like a table. And this is what we're going to do for all these problems. And if you trust me and you follow what I'm giving you as a guideline, I promise you this will not get difficult. If you write chicken scratch all over the paper and you're not organized, you're going to lose your mind in these problems because you need to be organized here. Now, and this is the approach I've always taken with this. This is the approach my high school physics teacher showed me, actually. The directionals can be thought of independently, completely and separately independently. So list your givens for each direction. Try it on your own real quick. List some givens for each direction. What's the x value numbers? Can I write down what's my acceleration in the x? What's my acceleration in the y? What's my displacement in the x? What's my displacement in the y? What's my time in either case? What's my initial velocity in either case? Do I have a final velocity in either case? List what you know in either direction. Try it on your own, see where you can get. Spend about 30 seconds, read through the problem, list what you think you need to write down.
So is this kind of something
No, it's not a proof at all. It's not even anything like a proof at all. This is what we did in section 3.1 and 3.2, where I told you list the givens, list the desired variable, and then put the equation. But we're just doing it with two directions. That's the reason it looks like a table. It's not statement of reasons. It's not a proof whatsoever. Trust me. Tell me something we know in one of these directions. Tell me something we know in one of these directions. Nick, what do you got, Nick?
I put for where it started, so would the x value be 0 and the y value be 300?
All right, I like where you're at. I would agree that the y value involves 300 for sure. Now, what is the definition of x and y in these cases? It's the change in the object's position. That's what displacement is. So you're on the right track. Did the object change positively or negatively?
Negative.
Yeah, so for the y, what should I put?
Negative.
Yeah, so for the y direction, we'll say that it fell, or negative 300. That's the displacement in the y direction. Now again, imagine the person or the point in space as the origin. Does he move to the right or to the left in the x direction? You could think of positive or negative. Yeah, it's going to be positive 50. So again, if you need to do this, go ahead and draw this if you'd like to. Maybe draw yourself a little xy axis to keep track of what's going on. And think about where he's moving. He's moving positive in the x, but which way? Negative in the y. Do you see what I'm saying? Use your quadrants as your directionals like with vectors, the same way. Think of the person as the origin. For once, you could think of somebody could think of themselves as the center of the universe. Okay, think of them as the center of the actual spot. Track the path of that origin as they go through. What else? What else do we know?
Like he's accelerating in the y?
In the y, he has acceleration. I would agree totally. And what is that acceleration around?
Gravity.
What is its value? Specifically? More specifically?
Negative.
Good. This is always going to be negative for projectile motion. Again, recognize, guys, in class, I tell you a lot of things. That's one of the things I told you. And then several people use positive 9.81 on the test because on the formula sheet, yeah, it does say positive. But I made a point to say, on the formula sheet it says positive simply because later in the year we're going to use it as positive. But with projectiles, we have to consider the motion, and the motion is down. Gravity is an acceleration pulling you down, so it is negative. Okay? G is negative. So again, that is AY. What does this Y mean here? What is this? Is that a variable?
It's acceleration in the y.
So what do you call this again? From chemistry, what was it called? A number below the actual variable? Subscript. It's your subscripts. Know that these are subscripts. Clearly make sure you do not put A and then a Y as if Y is a variable. This is not Y, the displacement you see above. This is displacement. This is just indicating the acceleration in the Y direction. What's the acceleration in the X direction? What's the acceleration in the X direction? We said we're going to assume there's no air resistance. No air resistance at all. Imagine a world with no air resistance. Would there be anything to stop you? So what's the acceleration? 0. Very good. You'd move constantly. It's always going to be 0. Write yourself a note right now, please. Highlight that. That will always be 0. Okay? Put a little asterisk for projectile motion, I'm saying. Okay? For all projectile motion cases, this will be 0. Now, if you do want to account for air resistance, or if it's a rocket with a propulsion in the back of it, yes, you would have AX for sure. The rocket would propel it forward, so there would be acceleration in the X. It's an unknown. It's an external force creating the acceleration. But we're going to assume, remember, we're going to assume for now that this can be considered negligible. So we're always going to have a 0 there. Make sure you put that note. Now, once acceleration is 0, tell me, look at your formula sheet. What's the only formula so far you've used that doesn't have acceleration? What's the only formula so far in your formula sheet that does not involve acceleration? There's only one so far. Out of the ones we've looked at so far, there's only one that doesn't have acceleration. Come on, what is it? What is it?
Velocity equals acceleration.
Very good. Constant velocity is equal to displacement over time. This will be the formula that we will definitely use. This will be the formula that we will absolutely definitely use in the X direction all the time. All the time. That's what makes this actually relatively simple. You don't even have to pick. This is always going to be the formula you're going to use over here. Okay, now, it depends on what we're solving for. It depends on what I'm solving for. Do I have V? Do I have velocity? No, I don't, unfortunately. Do I have time? I don't, unfortunately. So how many variables am I missing?
2.
So how many equations do I probably need?
2.
Where do you think I'm going to get the other equation? Use your context clues. What's that? From the y direction. And we will link them together. Remember how you did substitution method in that summer math packet? That's where it's going to come into play. The first time. You're going to see substitution like 7 or 8 times this year in different topics. But this is the first time you're going to see this. Now, this V bar I wrote here. See this V bar here? What does that bar above it mean again? What did I say? Constant. In what direction are we in this case? Yeah, but in specifically, the vertical or the horizontal? This one is the horizontal. So we could also do this. And that might be very useful to do that throughout the year. To recognize that the velocity in the X direction is always a constant. So, again, Tom Cruise did what? He ran off a bridge. He ran off a bridge horizontally to save himself from something. Horizontally. So the velocity with which he ran off the bridge is in the X direction. So in the end of this problem, our goal is to find V bar X, the constant velocity in the X direction. It's not going to change. This velocity will never change. The velocity over here will indeed change. What's the initial velocity in the y direction? What did we say? 0. Because remember, this is like a free fall because he's moving horizontally. So look what my subscript looks like now. See 2 letters there? I stands for initial. Thank you, Will. I stands for initial. And then the y obviously stands for the y direction. So again, visualize, please, visualize. Here's Tom Cruise. He's running off the bridge. His velocity is only horizontal. It is only horizontal until he falls off. And then, after he falls off, it becomes vertically negative. You follow what I'm saying? So if we had a VF, or if a problem involved VF, the answer in the y direction will absolutely be negative, assuming it's falling down. Now, later on, we're going to throw things up, we're going to launch objects up, and we're going to see that on the way up, the velocity is positive in the y, and then it becomes negative in the y. But again, this will not change. Why will this not change? Because acceleration is 0, and that's very convenient. That's the reason this will be a constant. You cannot have a change in velocity if you don't have acceleration. When you don't have acceleration, you don't have a change in velocity. Okay? Let's go ahead and take a look at what we can do now. In the y direction, that's all I know. That's all I've got. Can somebody give me a formula that could be useful, that I could use in the y direction, that I could then solve for something in the y direction to bring over to the x direction? There's a variable that's the same in both directions. There's a variable that's the same in both directions. Anyone know what that variable is? No? We got x is separate than y. Look, they're different. See, x is horizontal, y is vertical.
Is it acceleration?
Not acceleration. Look, these are, remember, they're labeled. They're different things. So both those answers, guys, they're different things there. The what?
Final velocity?
No, technically you can think of them separately also. You can calculate the velocity of this the whole time, find the velocity separately. You can put them together to make one velocity.
Can you repeat the question? Isn't it the time?
It's the time. It's the time. The question was, oh, sorry, Guillaume, I'm going to repeat the question. The question was, there's one variable that is independent of direction. It's time. The time it takes this object to move vertically is the same time it takes it to move horizontally because it's one object. It's not two objects, really. Time is not broken into components. The time in the x and the time in the y, time is time. It's the same thing. This object falls from here and it lands on the ground. The time calculated, whether you do it in the y or the x direction, needs to be the same because it's the same object. So time is what we call, write this down, our linking variable. We're going to use that term again later in the year. We're going to use time as our linking variable. What do I mean? Why would I call it? Yeah, absolutely. Why would I call it a linking variable?
Because it's used for both x and y.
Exactly. It's going to link our directionals together. It's going to link our horizontal and our vertical motion to one another. Is that enough?
Yeah.
Now, what equation could I use in the y direction that also involves time? It involves those three variables, vi, acceleration, and y, and it also involves time. Look at your formula sheet. You don't look at me. I can't telepathically give you the answer, right? You have 4 formulas. Look at the formulas. Figure out, no, on your own for now, because clearly not enough people are doing this or know this. On your own, for a second, look at the formula sheet. Write down the formula you would use that involves these 4 variables. I want to prove to you that once you have all your givens correct, it's actually an easy problem. This is just simple algebra at this point. I know it seems like it's difficult, but right now all this is algebra. Once you do all this, this is the hard part. You've done all the hard work. The hard work is over. Will?
You just take y vit plus half of at squared.
Very good. Well done. Now, in these problems, we have y equals vit. This vi is really viy. I don't care whether you use these subscripts in the formulas or not, but please don't confuse them for variables when I use them, okay? I'm going to show them here. If you don't like to do that, that's fine. Some students last year got confused by it. But I'm always going to put subscripts because I know I'm looking at my y direction right now. So viy is one entity. It's a quantity, 0. So what do I do when something is 0? Do I care about it? If something is 0 and it's going to multiply other things, do I really care about it? Because 0 times anything is? Thank you. So I'm going to plug a 0 in right here to show you, oh, 0 times time is 0. That drops off. So put that little symbol. Remember I showed you the symbol? It just means it goes to 0. Okay? You could just drop it off. You don't have to put that symbol. I don't care. It doesn't matter. You could do this. You could just simply go right to the next line. Now, looking at this formula, you know y. That's the vertical displacement of negative 300. You know ay. That's negative 9.81. You could easily solve for time. You could easily solve for time. You can choose if you'd like to plug in numbers now or solve algebraically for t. I'm going to solve algebraically for t. So to get rid of 1/2, I multiply both sides by 2. The 2 and the 1/2 cancel. I've got 2y now equals a sub y t squared. If I want to get rid of a sub y, I'm going to divide by it. I'm only showing this now. I'm not going to do this in the future, FYI. Those cancel. So I've got 2y over a sub y is equal to t squared. When I have something squared, how do I get rid of the squared? Square root it. That could be a generic solution. And you might have seen this solution when you did your problem set, because a couple problems that were dropped from rest, if you wanted to calculate time, that was the exact same solution. It was radical 2y over a. Again, it was radical 2y over a. Plugging in numbers, y is negative 300, ay is negative 9.81. Plug those numbers in, calculate what's going on under the square root. Then go ahead and square root it. We're going to get, what are we going to get? Can somebody tell me what we're going to get? Again, you guys need to do the math parts here. Come on. Yeah, right. What do you got? Radical 61.2?
Yeah.
Give me to the nearest like hundredth. Give me a couple decimals. 7.8. What do you got? 7 point. Can you give me one more decimal? Just because we're going to use this number in a moment.
7.82.
All right. See, again, we're going to use this value in a little. Where are we going to use it? It's our linking variable. So we're going to link it over to the x direction. We're going to link it over to the x direction. So 7.82 is our time. Let's go over here and write that down now. All that work in the y direction, only to move it over to the x direction. Now we can plug in time here, we can plug in x here, and we can solve for Vx. That was the velocity we were trying to figure out in the first place. It's 7.82 seconds. That's not a 5 at the end there. And my units perfectly match up. It's meters, 50 meters over 7.82 seconds. What do you got, Amaya? I see you calculating. You got the other one? All right. Anybody got this one? Simple math. Type it in. Hit enter. Don't be lazy. What do you got, Nick? 6.4 meters per second. 6.4 meters per second. Again, this is the velocity with which he ran off the bridge. Now, listen real quick, because I know the bell's going to ring. The homework for this section, you can't do it all right now. You cannot do it all right now, but you can do what's called horizontally fired projectiles. So if a problem involves an angle for now, don't do it in the homework. But you can do the problems that don't involve angles. You see what I'm saying? If it's launched at an angle, don't do that yet. If it's launched horizontally, practice that one tonight, please. Jake. And for those who are thinking, maybe outside the box, yes, you could have taken this expression actually here and plugged in for time. Instead of getting a number, you could have taken this whole expression root 2i over a and plugged it into the formula itself. Think about that, Hudson. It's a little bit different aspect, but it works better.
So I put 3-4 in my slide.
Okay. And when did you actually have it done? That's what I need to know.
October 3rd.
It says it on there and everything? Thank you. Because it wasn't in there, just so you know. It wasn't in the drive earlier. Weren't these the good old days of physics, right? Projectile motion? I loved it.